This is part 1 of lesson 3.2, exponential equations. So learning how to work with exponential equations, we are going to do some story problems. And so the first thing we always need to decide is it growth or decay? So we have to look at a problem and decide, is it going up or is it going down? Because that's going to affect which equation we use. We need to ask ourselves, is it involving money? Is it compound interest? So all of those different things kind of weigh into our decision. So we'll talk more about compound interest later, but the other things we've talked about. So the first question, it says a certain bacteria quadruple. Okay, there's a special word right there. Every half hour. So every 30 minutes. So if a sample has 5 bacteria, so that's to begin with, so I'm going to put the 5 right there. How many bacteria will there be after X hours? And notice that there's a time discrepancy there. Half hour, hours. So if we think about what happens, every half hour we're quadrupling, so it's doing this. That's not the same as saying, since it's an hour, it's not saying times 8, because 5 times 8 would be 40, and so that's not what that is. So we have to be really careful about our time frames. And so let's think about what's going on here. So go ahead and fill in the rest of the table, and label your X and Y axis, and then come back and we'll answer the rest of the questions. Okay, so you're supposed to fill in the rest of your table and label the X and Y axis, and so you should get the numbers that I have there. Notice that every half hour it's times by 4 every single half hour. Now every hour, it's not just multiplied by 8, because that wouldn't be the same thing. So 80 times 8 is not 1280, so it's doing more than that actually. So we need to be careful that we're not just assuming that because that's half an hour, 2 of those is an hour, we're just going to double the 4 times. So quadruple isn't going to turn into 8. So filling in the table, we've done that, and we need to graph it. So let's go at 0, we're going to have 5 bacteria, so that's hardly anything. And then at half an hour, we're going to have 20. And at 1 hour, we're going to be up to 80. And then at 1.5 hours, we're already up to 320. And then at 2 hours, we're up to 1280. So after that, we can't even graph anymore in this graph. We don't even have any more. So how many times has the bacteria quadrupled in 1 hour? So in 1 hour, it's quadrupled once, twice. So the answer to that is 2. Okay, so how many times will the bacteria have quadrupled in 4 hours? So in 4 hours, if every hour it's quadrupling 2 times, and in 4 hours it's quadrupling 8 times. So if I look at my table, I've got once, twice, 3 times, 4 times, 5 times, 6 times in 3 hours. So in 4 hours, it's going to be 2 more than that, so 8. So question comes up, how do I write the equation for this? So we've learned last time how to write equations for this. Is this equation accurate? So you can try, does that work? If I do 5 times 4 to the 1 power, does that give me what I have in an hour? Does that work? So the answer is no, that does not work. So the question is, how do I change the equation so that I can represent what's happening? So look at the answers to these questions right here, and I want you to think about how can you change that equation so that you can plug in how many hours and you have an accurate equation. So pause the video and think about that and write something down, and then come back and see how you measured up with your guess. Okay, first off, the equation doesn't work because it's not quadruple. Well, we'll say this only makes it quadruple every hour instead of every half hour. So how can we change the equation to represent the situation? If I want 1 hour, that's going to mean that I'm going to quadruple twice. 2 hours is going to mean I'm going to quadruple 4 times. 4 hours is going to mean I'm going to quadruple 8 times. So what would X hours mean? What am I doing to each of these numbers? So look at the pattern that's happening, and I see that if I have 1 hour, I'm going to go 2 times. 2 hours, it's going to quadruple 4 times. 4 hours, 8 times. So then the question is then, if I have X hours, it's going to do this how many times? And so the answer is 2 times whatever X is. That's how many times it's going to quadruple. So number 6 is a really important idea. It says the exponent does not always represent how much time has passed, but what it really represents is the number of time periods that have passed. So depending on what the problem is talking about, like in this case it says that it quadruples every half hour. So in this problem, a half hour equals 1 time period. And so that's really important as you get through some problems. You have to pay attention to what the time periods are that they're talking about. So the correct equation for this one would be y is equal 5 times 4 to the 2x power. When you type that in your calculator, you're going to type in 5 times 4, and then to the power of, now since you've got 2x, if you don't put parentheses around it, your calculator is going to be doing this part first, and then multiply times the 5, and then multiply by the x. It's not going to give you the right answer. So you need to be super careful. You need to be super careful that you're typing this in the correct way, because your calculator can't read the problem. It doesn't know. So what you need to type in is you're going to put parentheses around that part of it, and then you'll get the right answer. So check that. Try a couple numbers from the table up above with your calculator, and make sure that if you do 2.5, do you get 5,120? So when you type in 5 times 4 to the power of 2 times 2.5, do you get 5,120? So make sure that that happens. Now back to the graph, I had these different time frames of bacteria. If I'm just graphing the table, then that would be enough. But if I'm graphing the equation, then I'm going to connect the dots. So for our purposes, what we're going to do, we're basically going to always just graph the equation that represents what's happening. It doesn't mean that it's going to be true for every single number. So like, this might be true like, in 45 minutes, it might be right there. But we're not going to worry about the continuity of the graph so much right now. We're just going to graph the equations that go along with it. Okay, let's go to the next problem. It says a population of mice triples, there's a word, every 4 months. So this is 1 time period. 4 months is a time period. A nest starts with 2 mice. So the first question, and this is a really important one to answer, is how many time periods are there in 1 year? So how many months are in a year? And how many sets of 4 months are in a year? So since we have 12 months in a year, there are 3 time periods in a year. So when I do my equation, I'm going to have to consider that. So number 9, it says write the equation, show the number of mice after X years. So I'm going to write, come down here so I have room, y equals, so we know we start out with 2 and we know that it's going to triple. So that part's the easy part about doing the equation. As far as doing the exponent, that's where we really have to stop and think. So if I have 1 year, that's 3 time periods. If I have 2 years, that's going to be 3 time periods and 3 time periods, 6 time periods. If I have X years, that's going to be X times, look at what I did, times by 3 times by 3, so it's going to be 3X. So it's going to be to the power of 3X, and that's how you're going to write your equation. Now when you put that in your calculator, remember, you're going to say 2 times 3 to the power of parentheses 3X. And so you can plug in these numbers one at a time, and you can get your values. So I want you to pause the video, and I want you to fill in the table, and then we'll come back and see if you got it right and go to the next question. Okay, I've got my table filled in. A couple things to notice. I did round right there. And one thing that you may notice also, depending on how you worked on your calculator, but these numbers are also rounded. So we're just rounding to the nearest mouse. We're not going to do parts of mice. So just round to the nearest mouse. When we're filling in tables, the table, and probably you should write this down. Your table, when you make a table, it is just a tool. It is a tool to help us graph. It's a tool to help us see the patterns. And so the table, if you're going to be rounding to something, it's not going to hurt that much, especially if you're going to graph it. If you're going from 281 mice to 1,458 mice, you're not going to notice if it should be like 0.2 or something like that. It's not going to matter, because when you look on the graph, it's not going to be enough to matter. So the table is just a tool, and so generally speaking, I will have you round the numbers in your table to a certain place value, so pay attention to that place value. Okay, the next question, Bond Savings Bond earns 3.5% in simple interest per year. Now we're going to talk about different types of interest. For right now, simple interest is like it sounds, simple. So for example, how that works is if you have $100 and you get 3.5% interest, remember, we never do math with percents. You always change that to a decimal. So if you have 3.5%, that changes to 0.035. You have to move the decimal 2 times left because you're dividing by 100. Okay, like percent is a percent out of 100. So dividing by 100, you move the decimal twice. So this is at the beginning. And so at year 1, you would take your $100 that you already have, plus you would get 3.5%. So what is 0.035 times 100? It's $3.50. And so you would get a grand total of $103.50 in your bank account. And then the next year, I'm going to get to keep the $103.50, plus I'm going to get another 3.5%, so 0.035. But this time, I'm going to do 0.035 of 103.50. And so that's going to be different. So every time I'm adding on something new, that's how interest is going to be working. So for right now, simple interest is just very simple. Okay, we're just adding on basically the same percent every year. Okay, so back to this question. Bond savings bond earns, so that's growing, 3.5%. So as far as what percent is that, or what decimal is that, it's going to be 0.035. And it's per year, so a year is a time period. Now, the reason that this problem is a little bit different, it says the current value of the bond is this much, and 10 years have already passed. So I know that time is going to be 10 years, but the current value, that's how much it is now. The question I don't know is what was it originally. So in my equation, remember, actually we're going to do this one. In my equation, we've got y equals a times 1 plus r to the t power. Remember what everything stands for. This is my original value, and this is my result. And so for this problem, I know what the result is. The result is going to be $536.03. What I don't know is how much I started with, so I'm going to leave a variable right there. 1 plus my rate, and then to the 10th power because 10 years have happened. Now when I go to solve this, I'm trying to get a by itself. So it says a times this number right here. So I'm going to divide by 1.035 to the 10th power, and then that will cancel. So divide both sides by 1.035 to the 10th power. So put that in your calculator, 536.03 divided by 1.035 to the 10th power. So put that in your calculator. I want you to do this yourself and actually see how it goes. What I got, if you haven't gotten your answer yet, pause the video, get your own answer. Okay, what I got is 380.001. So if I'm rounding that for money, it's going to be $380. So that's how much Vaughn started with when he began his investment, $380, and now it's grown to $536.03. So that's one way to do this problem. Now, you can do this problem a different way. It depends on the perspective of time. So another way you can look at it is you can say, all right, right now I have $536. So $536.03. It grows at 0.035, so 3.5%. But I want to know what it was 10 years ago. So if I think about time like on a timeline, okay, when I did this problem a minute ago, I said, here's where I'm starting at, well, I don't know what I'm starting. I said, okay, I'm starting now, and I'm going to go for 10 years. So this is times 0, 10 years, I'm going to have $536.03. And so that's what I did just a second ago. If I change my perspective on the time, and I say, right now, after 10 years have happened, okay, so, sorry, right now is currently, and so I have $536.03, then what was this time back here? I had an unknown amount, and it was 10 years ago, so on a number line, that's going to be at -10. So if I do -10, what will that give me? So go ahead and pause this and put that in your calculator at -10. So 10 years ago, 10 years in the past, what does that give you? Okay, if you haven't gotten your own answer, I want you to get your own answer for this. Don't just wait to see what I have written down. So type that in your calculator. and you should get exactly the same answer that we had before, 380.001, and so that's the same exact thing. And so it just depends on your perspective. You can look at it different ways, but that's how you would do that problem. Okay, the next problem, a pendulum. So a pendulum, think about like a grandfather clock, and it's got this thing that kind of hangs down like that, and it goes back and forth like that, so it swings back and forth. Or if you have a ball on the end of a string and you swing it back and forth, that's a pendulum. It has a beginning height of 45 inches. So when you first swing it, I wish I could draw better, but if you have this string hanging down with a rock and it swings, so when you first swing it, it's going to go 45 inches high. And then it comes down, and then it goes back, but it doesn't go as high the next time. So the next time it's going to be less than that. And it's going to go down and back, and then it's not going to make it as high. It's like when you're swinging on a swing or something, you don't quite make it as high. It loses 8%, so that's a decay. So I'm going to use my decay formula. Loses 8% of its height with every swing. Write an equation to represent the height. So we're going to say whatever the height is, we're going to start at 45. Now what's going to go in there? Is it going to be 0.08? If you try that, you're going to go from 45 to nothing very, very fast. You're not losing 92%, which is what that equation says. You're losing 8%. So we need to say, I'm going to take my full height and take away 8%. And I'm going to do that x times. So that's the equation that you would use for this. You could also write y is equal to 45 times 0.92. That means that I'm losing 8%, I'm keeping 92%. That means that my decay factor, if I ask you that question, which you'll be asked that question on a quiz or a test, my decay factor would be 0.92. My rate of decay is a different question, and that would be my rate that it's decaying at, and that would be the 8% or the 0.08. So just so you know, that's going to be a test or quiz question, and those are two different things, so you need to make sure you understand that. But I can write the equation either way, so either one of these would be a good equation for that. Okay, and the last part of this one is, what is the height of the pendulum after 15 swings? So once it swung back and forth 15 times, how high is it going to be? How many inches? So you're going to write that equation. So on your paper you write that, then you put it in your calculator. You don't just put it straight in your calculator and not show anything that you did. So you need to show what you did on your paper before you write down the answer. So I know you're putting it in your calculator, but I want to see how you're putting it in your calculator. And since I'm not watching your screen, you have to tell me on paper. It doesn't say how to round this. At least I don't have that written down. And so 12.88 inches, and that is rounded a little bit. Depending on what it says, you might say it's 13 inches if it says round to the nearest inch. If it said round to the nearest tenth of an inch, it would be 12.9 inches. So it's just going to depend on your rounding directions. If there's no rounding directions, then you can use your best judgment. But if there are rounding directions, you have to follow them. Okay, we're going to finish the rest of this lesson in part 2 of the video.